welcome to the deep dive. Today we are tackling a really important mission, I think. We're synthesizing the insights from a fascinating academic paper.
Right. It's called Characterizing Fisheries Connectivity in Marine Social Ecological Systems, and the lead author is Emma C. Fuller.
And our goal here is really to give you the shortcut, to understanding how fishing communities actually manage to survive in what's a constantly changing ocean environment.
It's a crucial piece of work because these marine social ecological systems, that's the environment, the tech, the management rules, all of it, they're always in flux. They're constantly shifting.
Yeah, and when those shocks hit, whether it's environmental or new rule, fishers don't just, stop. They have to adapt.
Exactly. And the paper really zeroes in on how they adapt.
And it's not just like moving the boat a few miles down the coast. The core argument is that a fisher's main survival tool, their main adaptation, is changing their entire professional focus, shifting which fisheries they target, maybe even the gear they use.
Precisely. And this choice, this behavior of switching targets when one fishery isn't working out, it creates these really complex, interlinked networks. It's all about alternative income sources.
The authors actually give it a name.
Yeah, they call it fisheries connectivity. Think of it as the hidden infrastructure of their economic survival. It's how they stay afloat, literally and figuratively.
And this really matters for policy, doesn't it? Because historically, management, like ecosystem-based fisheries management, EBFM, it's mostly looked at the food web.
Right, how species interact ecologically, who eats whom. But they've largely, maybe not ignored, but certainly underemphasized these crucial social networks, the human response.
And that's a huge gap.
It really is. Because if you don't understand this social network, this connectivity management is kind of flying blind. When a big disruption happens, maybe a sudden fishery closure or a bad climate year, policymakers can't accurately predict where all that fishing effort is going to shift.
Yeah, where does it pop up next? And there's a perfect, quite stark example of this in the source material itself.
You mean the West Coast salmon fishery closure?
Exactly. Back in 2008 and 2009, it was triggered by really poor returns at the California Central Valley Fall Chinook salmon the year before, in 2007.
That was a major crisis for those communities. And the key point the source makes is that the fishers who depended on salmon, well, they didn't just pack up and go home overnight.
No way.
Many of them, the ones who could, immediately shifted significant effort. They moved into albacore tuna, Dungeness crab, even various groundfish.
And that sudden rush, that mass migration of fishing effort, it perfectly shows this network effect in action. It put totally unexpected pressure on those other fisheries, the ones connected through the fishers' choices.
Exactly. It shows the real-world stakes. So, okay, understanding that background, let's get into the methodology. How did Fuller and her team actually map something so, well, messy? Thousands of individual fishing decisions turning into a network.
It sounds like a huge undertaking.
It was a massive data effort. They focused on the U.S.-California current large marine ecosystem, the CCLME, and they used commercial landings data from PACFIN, the Pacific Fisheries Information Network.
Which years did they look at?
Just 2009 and 2010. And they specifically chose that period because it was relatively stable. There weren't any major El Nino or La Nina events, no huge management shakeups. It gave them a kind of baseline snapshot of normal connectivity.
Oh, okay, so they have the data. How do you build a network from that? You have the points and the connections, right? The nodes and edges.
So the nodes in their network represent a fishery. But crucially, it's not just defined by the main species caught. They used a more technical term, métier.
Métier, what does that capture?
It's basically an objective cluster of fishing trips. They grouped trips together based on the specific gear used and the precise mix of revenue coming from different species in the landings. So it's about the whole strategy of that trip.
That sounds statistically complex. How do you group trips like that objectively?
Yeah, they used a statistical method involving something called the Hellinger distance metric. You can think of it as a way to measure how similar two fishing trips are.
Okay.
So if one trip brings in, say, 90% revenue from crab using pots and 10% from something else, and another trip is 80% crab revenue with pots and 20% something else, the Hellinger distance tells you they're very similar. Small distance means similar strategy.
Got it. So that defines the nodes, these specific fishing strategies. What about the edges, the connections showing the connectivity?
The connections, the edges, are formed by the vessels themselves. The strength or weight of the link between two fisheries, two métiers, depends on two things.
Okay, what are they?
First, just the raw number of vessels that participate in both of those fisheries. More shared vessels means a stronger potential link.
Makes sense. And the second thing?
The second is the evenness with which those shared vessels rely on both fisheries for their revenue.
Oh, right. Evenness. Why is that so important? Why not just the number of boats?
Because think about it. If a boat gets 90% of its income from fishery A and just dabbles, getting 10% from fishery B, it's not really connecting them strongly. It's mostly an A boat.
Right. It's not very diversified in that sense.
Exactly. But if a vessel splits its income, say 50-50 between fishery A and fishery B, that shows a much stronger, more balanced reliance. That balance indicates a really flexible, adaptive link between those two fisheries in the network. It's a stronger connection.
And crucially, they didn't just map this for the entire West Coast as one giant network, did they? They looked closer.
That's a key point. While they did calculate it for the whole CCLME for comparison, their main focus was analyzing networks at the port group level.
Grouping nearby ports together.
Yes, because that scale best represents the actual coastal fishing communities. That's the level where these adaptation strategies play out and where vulnerability is really felt.
Okay, let's move into the findings then. When they actually built these networks, what was the first big takeaway, looking across the whole CCLME?
Well, the immediate, perhaps unexpected finding was just how generalized the vessels are. They found that vessels in the CCLME are overwhelmingly generalists.
Really? Not specialists?
Not predominantly. Virtually every single fishery, every métier they identified, was connected to at least one other fishery through shared vessel participation. It really hammered home that diversification isn't just one strategy. It seems to be the dominant survival strategy along the West Coast.
So it's a highly interconnected web.
Yeah.
How did they figure out which fisheries were the most important hubs in that web, like the key intersections?
They used network analysis tools, specifically centrality metrics, things like node strength, between fangus centrality, fragmentation centrality. These measures help identify which nodes, which fisheries are most critical to the network's structure.
And were there clear winners? Or maybe, depending on how you look at it, the biggest potential points of failure?
There were two that consistently stood out across pretty much all the networks they analyzed: the Dungeness crab pot fishery and the spiny lobster pot fishery.
Okay, Dungeness crab, that makes sense. It's huge economically. Yeah. Spiny lobster, too, down south. But what does central mean here in network terms? Is it just about money?
Not just money, although that's related. High centrality here means a few things. High node strength means these fisheries are connected to a large number of other fisheries. Lots of vessels link through them.
Okay.
But maybe more importantly, they also scored high on fragmentation centrality.
Fragmentation centrality. That sounds significant. What does that tell a local manager?
It signals a major vulnerability. Think of that fishery as a crucial bridge in the network. High fragmentation centrality means if that fishery, that node, is hit hard, say, a sudden closure due to toxins or climate impacts its removal would cause the entire network to shatter into smaller, disconnected pieces.
Wow. So it breaks the pathways for other fishers to adapt.
Precisely. It severs those alternative routes. These central fisheries aren't just important for their own revenue, they act as the critical highways that many other fishers rely on to navigate change and shift their effort.
So Dungeness crab and spiny lobster are like major hubs for adaptation along the coast.
At the large scale, yes. But they also found this varies geographically, which is really important.
How so?
Well, if you look at specific port groups, the picture changes. Up north, say in Newport, Oregon, Dungeness crab is absolutely dominant in the local network structure.
Okay.
But shift down the coast to Santa Barbara, California, and suddenly the local network's key fishery is squid. And go even further south to San Diego, and it's the spiny lobster fishery that holds the central position locally.
So that heterogeneity, that local flavor, is critical for understanding community-level impacts.
Absolutely essential. A coast-wide policy might miss these vital local differences entirely.
That makes sense. Okay, so zooming back out from the individual nodes, what about the overall structure, the topology of these networks? Did that reveal anything about resilience?
Yes, it did. They looked at network-level resilience using something called the universal resilience function, and they found a clear pattern, a latitudinal gradient, meaning that port groups in the north, so Oregon and Washington, were generally more resilient to shocks than those in the south, in California.
Interesting. Why would that be?
The study suggests it mainly scales with economic size. Resilience seemed to correlate directly with the total number of vessels and the total revenue generated within that port group. Bigger, wealthier port communities just seem to have more systemic capacity to absorb shocks.
Okay. They also talk about something called modularity with a Q value. What's that measuring?
Modularity, or Q, measures whether the network naturally breaks down into distinct clusters or modules. Think of modules as groups of fisheries that are tightly interconnected internally, but have fewer connections between the groups. Essentially, distinct fishing strategies.
And is high modularity good or bad?
Well, that's the interesting part. It leads to what the authors termed the modularity paradox.
A paradox. Sounds like there's a trade-off.
Exactly. On the one hand, if a network has high modularity, it means it's less sensitive to directed shocks. If a shock hits one specific cluster, the damage tends to stay contained within that module. It doesn't easily spread to the whole network.
Okay, that sounds like a good thing. Lower sensitivity.
It is in that sense. However, the flip side is that high modularity also means low adaptive capacity for the fishers within those modules.
How so?
Because they're sort of stuck in their cluster, they have fewer connections, fewer pathways to switch to alternative fisheries outside their specialized module. If their main targets fail, they're constrained.
Ah, I see. So management faces a balancing act, encouraging specialization, which might increase modularity, versus maintaining broad flexibility, which might decrease it but enhance overall adaptation.
Precisely. It's a really neat conceptual challenge for managers.
That's a powerful idea. But maybe the most eye-opening finding, for me at least, was how this social connectivity relates back to the traditional ecological view.
Oh, absolutely. This was a key confirmation. The study showed definitively that these social dynamics, just the human behavior of fishers choosing where to fish, create strong network connections that are completely independent of the underlying food web.
Wait, so fishers can link species through their activity even if those species never interact in the ocean?
Exactly. The connectivity created by vessel participation can link species that have zero direct ecological connection.
That feels like a fundamental shift for EBFM. What's the classic example they use?
The link between albacore tuna and Dungeness crab. Think about it. Albacore are pelagic. They swim near the surface, migrate long distances. Dungeness crab are benthic. They live on the seabed.
Totally different parts of the ecosystem, no interaction.
None ecologically. Yet they are strongly connected in the fisheries network constructed from vessel participation data. Why? Because the same vessels often target both, maybe seasonally. The social link forged by the fishers creates a network connection that bypasses the ecological separation.
Wow. Okay, that really underscores why you can't just look at the biology. Let's move into the broader implications then. What does this mean for how we govern fisheries?
Well, the big one stems from that heterogeneity we talked about. Because things look so different at the port group level compared to the whole CCLME, the authors strongly caution against one-size-fits-all management policies designed only at that large, coast-wide scale.
Because they'd likely be ineffective.
Ineffective or potentially even harmful to specific local communities whose network structure is different from the average. The blanket approach just doesn't work here.
So what's the alternative? How should governance be designed?
They suggest using principles of polycentricity. That means multi-level, nested governance systems that can actually address issues across different scales, simultaneously, local, regional, coast-wide.
That sounds sensible, but probably hard to implement.
Very hard, especially given current institutional structures. They point out the constraints. For instance, a fisher might have a crab vessel, but digging into the data shows maybe 70% of their revenue comes from state-managed crab, while the other 30% comes from federally managed groundfish caught on non-crab trips.
Ah, so a change in federal rules could destabilize their income, which then forces changes in how they fish for the state-managed species.
Exactly. The jurisdictions are separate, but the fisher's economic reality links them tightly. Polycentric governance would ideally try to bridge those gaps.
Now, this study was based on just 2 years of data, 2009-2010. They acknowledged that limitation, right? What's the risk of using such a short snapshot?
Yes, they were clear about that, and they made a very strong case for needing much longer time series data, decades, ideally.
Why decades? What are you looking for over that longer term?
One key reason is to monitor for a potentially dangerous phenomenon they call the gilded trap.
The gilded trap? That sounds worrying. Like fool's gold.
Sort of. It describes a process where fishers might get drawn into and then locked into a fishery that's initially extremely profitable. That's the gilded part.
Okay, high profits attract effort.
Right. But that high profitability can drive increasing specialization. Fishers might invest heavily in gear specific to that one fishery, maybe sell off permits for other fisheries they used to participate in. They become more and more reliant on that single lucrative stock.
Reducing their diversification, their portfolio.
Exactly. They lose their adaptive capacity over time. So when that single fishery eventually faces a downturn, maybe a natural fluctuation, a stock collapse, or new regulations, they're trapped. Their sensitivity to that specific shock is massively increased because they've lost their alternative pathways.
That makes sense. You need long-term data to see if communities are slowly sliding into that kind of trap.
Precisely. It's a dynamic process.
So looking ahead, what did the authors see as the ultimate next step? The holy grail, perhaps, for really improving ecosystem-based fisheries management using this network approach.
Integration. The crucial next step, they argue, is to link these social connectivity networks, the ones based on vessel participation that they mapped with quantitative descriptions of the ecological networks, the food webs.
Connecting the human behavior network with the species interaction network.
Yes, creating what they call end-to-end social ecological network models.
And what would that allow us to do?
That holistic view would allow managers to finally trace these complex, multi-step feedbacks through the entire system. For example, you could model how a purely social change, like a new license rule affecting fishery A, forces fishers through the social network to shift effort into fishery B.
Which targets a species that might have no direct ecological link to fishery A's target species.
Exactly. But that shift could still have unforeseen ecological consequences down the line, maybe impacting the prey or predators of species B. Being able to identify and predict those kinds of indirect, cascading impacts across the social and ecological realms, that's critical for truly systemic management and understanding real vulnerability.
Yeah, what really stands out to me from all this is how it reframes the whole issue. We often think of fisher behavior as purely a social or economic factor, separate from the ecology. But this research shows it's actually a critical and, importantly, a measurable component of the ecological system's stability and the community's resilience. The future health of marine ecosystems might depend just as much on understanding the networks of human adaptation as it does on traditional food web models.
It really puts human adaptive strategies right at the center, perhaps as the biggest source of uncertainty, but also potential resilience in these marine systems. A powerful shift in perspective.
Thank you for joining us for this deep dive.